My name's Christy. I'm Deputy Director here at the Isaac Newton Institute. I'm actually in the Isaac Newton Institute. And I can't tell you, I open many, many workshops, and it gives me more pleasure to open this one than almost any other workshop, because the building has been empty for so long, and this has been really in planning for such a while. So back in 2017, during the Big Proof program, Shankar and Tony Hoare got together the idea of running a verified software program and ran it past me. And I said, absolutely go for it. And I gave them, I think it was about a week's time to put together a preliminary proposal, which they did breakneck speed. They got it in on time. It got accepted and recommended for putting in a full proposal, which they got in time for the next round. And sure enough, that got accepted first time round. And so the program was scheduled to start on the 27th of July of last year. I was hugely excited about it. And then suddenly the world all changes and it needed to be postponed. So it's going to be now running, as you all know, from the 4th of July in 2022. And we now have 2 bridging workshops just to fill the gap. So the first one is verified software from theory to practice. And then the second one from the 7th to 11th of June is tools and experiments. And that will include a special event to mark Tony Hoare's invention of quicksort. And that brings me nicely on to why this is particularly exciting and wonderful for me, that we will have this, that we will be running this program, that we will have you all in the building. Because almost exactly 24 years ago to the day, Tony Hoare interviewed me for first my MSc and then my doctorate in Oxford in theoretical computer science. So this is really dear to my heart. My research was in semantic models. I defined and identified a family of failures-based models for describing concurrent systems and explored how existing tools could be used to formally verify these models. So as you can see, this workshop is very, very dear to my heart. But we have one slight problem, which is when we look at the timetable, Tony is meant to be speaking next. And he is having difficulty connecting. I'm about 10 minutes away from where he is now. So forgive me, I've literally, you might have noticed, just before I started talking, I was on the phone to Tony. And I am going to run to his house and see if I can set up his Wi-Fi connection. And so if you bear with me, I will disappear momentarily. And I hope that Shankar might have lined up the next speaker. And then hopefully that I will get Tony ready for you all to speak in a moment. It's not quite the technological way that we normally do it, and I'm running to someone's house. But anyway, hopefully it might work. And Shankar, is that sorted? Have you let the next speaker know how we might do this?
Yeah, I just want to check, Maurice, would you be willing to go ahead with your presentation?
Yes, I'd be happy to. And it's always a relief not to have to follow someone like Tony. So I can,
I apologize for stitching you up on this. It was just an on-the-fly solution that I came up with just a couple of moments ago. So
makes perfect sense.
Thank you, fantastic. So if you don't mind, I'm all going to now sign off, hand over to you, Shankar, and hopefully I will see you all from Tony's house presently.
Thank you, Christy. Yeah, and our chair for today is Azadeh Farzan from the University of Toronto. So, Azadeh?
Yes, so Maurice, while you share the screen and set up, I'll let everyone know that the meeting is being recorded, as you can see. If the live subtitles are bothering you, there is a CC button in the lower part of your screen. You can click on that and you can turn it off so that you don't have the subtitles or live transcripts. And if you don't wish for your image to be shared, but you still would like to ask a question, you're welcome to turn your video off, your camera off, but still speak. And if you don't wish to do either, you can type the question in the chat and I will ask the speaker the same question. And otherwise, you can type your questions, you can raise your hands. We try to go through as many people as possible, hoping for a lot of participation. And Maurice, is sharing going well, or?
Sharing is proceeding.
Great.
Also, Maurice, can you speak up into the microphone?
Okay.
Great. So our first talk is Maurice Herlihy from Brown University. And he doesn't need really any introduction, very well known to everyone. So I'll let him kind of use his time to share with us.
Great. Can you see my screen?
Yes.
Okay, great. So I spent a wonderful year on sabbatical in Cambridge, and it breaks my heart I can't be there haranguing you all in person, but I'll do my best. Now, I'm a little bit of an imposter here because I don't produce verified software, but I consume it. So that is to say that I'm not a chicken, but I have opinions on omelets. Now, the particular thing that I'm interested in is how to deal with things like blockchains. So I'm sure you've all heard about blockchains. I'm sure many of you have distorted ideas about the lurid and sensationalistic aspects of blockchains. But I want to focus here on this scientific aspects. So as far as we're concerned, a blockchain is just a distributed ledger. It's an append-only list of events, very simple notion invented during the Italian Renaissance. These events can be financial events. It can be things like database updates. It can be file system logs, all kinds of things. The magical aspect of these things is that everyone agrees on the content. The ledgers are tamper-proof. They're distributed and tamper-proof. And this means that you can use this to deal with people you don't trust. So that even though you know that either one of you would happily pick the other's pockets, you don't need to worry that they're tampering with the ledger. Now, the interesting part of ledgers are what are called smart contracts. Now, smart contract is a little bit of a marketing hype because smart contracts are not smart, and they're definitely not a contract in any legal sense. What they are finite state machines, a little bit like vending machines. So what does a vending machine do? Well, Alice goes up to the vending machine and she puts in a coin and gets something back. In a blockchain, instead of putting in a coin, you might put in a cryptocurrency and you might get back some kind of a financial instrument. The principle is the same, even if the objects being exchanged are much more exotic. Technically, a smart contract is something that controls assets. In the vending machine case, it hangs onto coins and it holds bottles of soft drinks. A smart contract on a blockchain can dispense cryptocurrencies. It can dispense tokens, assets, all kinds of things. And it's a stateful program. The fact that smart contracts are programmable adds a huge amount of power to blockchains. So blockchains without smart contracts are, in some sense, not all that interesting. Once you have the ability to program things, then it becomes much more interesting. Smart contracts, the code is public on the blockchain, so everyone can see what the contract will do, at least in principle. So this level of transparency means it can be trusted. So that if you and I want to make a deal using a smart contract as an intermediary, I might not trust you and you should not trust me, but we can look at the code on the blockchain and the code will tell us what will happen. Now, the particular application that I'm interested in here is called DeFi, in other words, decentralized finance. There are plenty of other things you can do with blockchains that are also interesting, but DeFi is a particular interest for verification. Now, I should mention that verifying smart contracts is not an obscure or unheard of area. There's a lot of work going on. I Googled verifying smart contracts, and these are the first 4 papers that appeared. So this is an active area, but my mission here is to call your attention to it. And any of you who might be looking for applications, this is an ideal application area because there's a lot at stake and there's a lot of funding available. So the reason smart contracts are interesting is because the state of the art is pretty bad. So here, talking about decentralized finance, the most popular smart contract language is called Solidity. And here's a headline that says that Solidity errors have gone up in 2020. Now, can you imagine Barclays Bank or Bank of America announcing Java sees significant uptick in security errors? This is a kind of, it would be astonishing to see that for a mainstream language, but this is commonplace in this area. So there's a huge need for more rigorous formal methods. Now, here's what I think the heart of the problem is. So I come from a background in distributed computing, and people in distributed computing, when they write algorithms or protocols, they think in terms of adversaries. We're very concerned with fault tolerance, and so we think, well, suppose imagine that we have an adversary whose sole purpose in life is to frustrate our intentions. So the adversary might be able to fool with timing. It might make messages arrive late or out of order. It might be able to crash some of your servers. You might lose some messages, or you might have Byzantine failures. Now, I'm going to argue something which is, people will dispute this, but nevertheless, I'm right and they're wrong. That our classical notion of Byzantine failures doesn't really work all that well in adversarial environments where your adversary is a person. Now, in today's world, especially if you're dealing with decentralized finance on blockchains, the adversary isn't this cute little demon with restricted powers. The adversary is, some collection of people sitting around a cafe in Central Asia, trying to figure out how they can steal all your assets. And so the 20th century adversaries are intelligent. They're often highly financed. They could be individuals with a lot of time on their hands. They could be government agencies. They could be organized crime. They could be all kinds of things. Now, one thing the adversary can do is to trick your smart contract into giving away your assets. This is sort of the most obvious way in which you can be attacked. Somebody can steal your money by exploiting a bug or an ambiguity in the contract. A more subtle attack is that your adversary might be happy to lock up your assets forever. And as you can see from this headline, this kind of thing actually happens. It happened quite recently. It's happened, multiple times. A more subtle attack is a denial of service attack. An adversary can just waste your resources by asking you to do 1 million 1 cent transfers, all kinds of things. And often, things like denial of service and perpetual lockups are not, in some sense, classical notions of failures that you get when you reason about, Byzantine agreement and other kinds of distributed computing issues. The most common programming language for smart contracts is something called Solidity. Now, I'm going to pick on Solidity a little bit, and it always seems a little bit unfair to pick on a programming language when the problem isn't so much the programming language as it is the programmers. But I'll make an exception for Solidity because it's a little bit exceptional. So this is language based on JavaScript. Now, as all of you know, I'm sure quite well, JavaScript is a language intended for web page presentation, a task at which it excels. And when you're presenting a web page, odd complex behavior is considered normal. Lots of different browsers, lots of different form factors, strange things can happen and nobody cares very much. And there's no precise notion of correctness if you're displaying a web page. So JavaScript doesn't lend itself to naturally to formal verification. The main reason that JavaScript exists is that it's easy for non-experts to write programs. And the programs will do things fairly quickly, and you can experiment with programs until you're happy. And there's no actual adversary. However much you might, be unhappy with, Google or Microsoft when you're trying to use their browsers, they're not actively trying to make your life difficult. Now, my claim here is that combining a web scripting language with distributed, decentralized finance is a little bit like mixing up, liquor and guns. You might enjoy one or you might enjoy the other, but putting them together is often not a great idea. So we probably don't want to use a web scripting language for irrevocable financial transfers. Small errors can be catastrophic. Precise definitions matter. Corner cases matter. And this illustrates something that I'm sure all of you know, is that designing languages is hard, but everybody thinks they can do a better job than the professionals. Again, it's a little bit like being a restaurant critic. So I'm going to give you an example. Those of you who are familiar with blockchain lore have probably seen this a million times, and so I apologize. But this is more an example for the general public. A few years ago, a group of people got together and decided to set up something called a DAO, a decentralized autonomous organization. The idea is that this would be an organization, kind of a venture capital firm that would invest in other businesses. They got about 50 million US dollars in capital in Ether cryptocurrency. And this was viewed as being kind of revolutionary because this would have no managers or board of directors. Everything would be done via smart contracts. And this plays into a kind of a libertarian vision where we don't need lawyers, we don't need courts, we don't need the instruments of government because we can write contracts that will do everything. We can look at the contracts, we can predict exactly what they're going to do. And in this way, we can kind of pre-agree on things and nothing can possibly go wrong. So the buzzword here is code is law. That what's written in the smart contract code is the law, and we don't need any other means of enforcing the law. The press loved this. There was much hyperventilation about the effect on the future of finance. All of these Wall Street rent seekers will have to go out and drive Ubers. This is the dawn of a new libertarian golden age, et cetera, et cetera. Let's look at a very simple example. So here, this is smart contract code. Again, it's written in Solidity, so it looks like JavaScript. The green arrow is the program counter. So here's a function where an investor in this DAO can withdraw some of their own money. So this is a function, is like a method in an object-oriented language. First it says, who is calling? Never mind the, odd syntax. Just keep your eye on the big picture. Question: does the client have enough money? The client asks for a certain amount of money. Do they have that? If so, send them the money by calling a function in their contract. What happens when you do this? That's what happens. So in some sense, I've already shown you everything that you need to know to see the error. The people who wrote this code were some of the people who founded the Ethereum blockchain. So they were probably the best qualified people in the world to do this. They're accomplished and famous people. So I'm not in any sense disparaging their programming abilities. So what actually happened? Well, here where this contract calls the other contract, It calls a function exported by the contract. What does it do? Well, this is the function. So the send money function increments its balance to credit its account. And then it does something weird. It turns around and it calls its caller back again without returning. This is called a reentrant call. And so now we have something that I'm going to claim is actually a concurrency error. Now, if you read the documentation on Solidity, they're very proud of the fact that we have no concurrency, everything is single-threaded, and it's all a lie. Here we have two program counters that are hovering over the same data at the same time, and that is textbook concurrency. And I don't have time to get into this, but I'm going to claim that the heart of the problem is related to the monitor invariant problem. The caller didn't restore the monitor invariant before releasing the lock. But so here, the bright green arrow is the current program counter. The gray arrow is the suspended program counter. So when we get down here, the contract says, does the caller have enough money? And the answer is, yes, they do, because we didn't decrement the balance yet. We returned the money to the caller, and then we decrement the balance. But when we returned the money to the caller made a reentrant call, and there's no sign that we've already transferred the money. So you can send the money again, and again, and again, and again, until eventually you run out of money. And in fact, this actually happened. Exactly this attack. This is not the kind of thing that you normally think about when you're debugging device drivers or writing a database code. This is something that really requires a malicious adversary to happen. It only happens because of the peculiar nature of the programming environment here. This reentrancy attack is not much of a threat today because everybody knows about it because it failed so spectacularly this time, although apparently these sorts of things do happen. But this is only an example. I teach an undergraduate blockchain course where I have 4 lectures of exploits like this exploit. These range all the way from profound insights to low cunning and overflows and things like that. But it's really a kind of state of anarchy. So I'm going to conclude with kind of a brief survey of points that I think are either controversial or maybe not so obvious. So a number of things in smart programming languages that you would consider normal and good in regular languages turn out to be problematic. So information hiding and modularity is almost universally considered to be a virtue. But if you think about what's the purpose of a smart contract? Well, two mutually suspicious parties have to agree on terms. And if you call another contract or you call an unsecured library, these are places where attacks can hide. So, for example, the fact that the contract that I showed you made a call to an external hostile contract, that's a form of information hiding, arguably, and that was where the vulnerability was. Turing completeness. This is a very controversial point, but what if we couldn't have unbounded loops? What if we couldn't have a recursion? When people talk about Turing completeness in smart contracts, they don't really mean Turing completeness in the usual mathematical sense. Basically what they mean is something that can't be statically analyzed. A non-determinism of any kind is
Did we lose the sound?
I think we lost Maurice.
Maurice, you froze, so can you perhaps rejoin?
I don't think he's in the call anymore.
I guess Zoom is not smart enough.
With dispatch, anything that makes it hard to do static analysis is bad. There's all kinds of correctness issues that, again, don't show up in conventional notions of correctness. Weak consistency is common in smart contracts, especially things that do, say, cross-chain transfers, complicated things. One of the problems that shows up, which is, I think, kind of scandalous, is usually the implementation is the specification. So this DAO exploit that I just described, a colleague of mine was interviewed by the FBI, asking him if this was actually a crime. Because in principle, all parties agreed to use this contract. The fact that someone found a way to drain the accounts that wasn't foreseen by the people who read the contract, that's a little bit like saying they didn't read the small print. And so it's not entirely clear that it's illegal to steal everyone's money if they leave a bug in their smart contract. This would be illegal in a real legal contract because the intent of the contract is important. But in the smart contract doesn't make any distinction between the intent of the contract and the actual code. So there is there's a lot of work that needs to be done there. And finally, the other thing is that attacks can range all the way from high-level contract details to details of the virtual machine to details of how scheduling works in the operating system to the way that storage is recorded. And that's because adversarial attacks don't respect abstraction. So this is not just about things like loop invariants and Hoare triples and so on. This is also about notions of atomicity, of scheduling priority. If someone can find a way to victimize someone else, by front running their transactions and things like that, they will figure out how to do that. So, in closing, I think that I'm calling everyone's attention to this because this is an area where there is a lot of reinvention going on. I became involved in this when I read a white paper by a company that had just raised an obscene amount of money. They were talking about their Byzantine Agreement Protocol. Their Byzantine Agreement Protocol didn't work. And it was also seemed kind of doubtful whether the people who wrote this understood what a Byzantine Protocol was supposed to do, and yet they just raised $100 million. So things are no longer quite this extreme, but it's still the case that if you come into this area with a solid knowledge in another area and you can recognize what's being reinvented, then you have a kind of a built-in advantage. So it seems to me this should be an awesome playground for people who want to verify software, because this is basically programmable money. The contracts are often not that complicated or not that large. There's a huge amount at stake. There's a huge interest in getting these things to work right. And there are all kinds of dramatic stories about cases where things have failed. And in that sense, this is way more interesting than something like cache coherence protocols, which I used to work on in earlier days. Everything is Byzantine. Everyone is trying to pick your pocket. It's a highly adversarial environment, and it really is, to me at least, distributed computing except with money. And perhaps to you, this is program verification except with money. And finally, as I mentioned in the beginning, blockchains have kind of a bad reputation because there's a huge amount of Ponzi schemes, ecological crimes, and so on being conducted. But underneath all of this, I think there is real science. And whether or not blockchains as such stick around it's always going to be the case that we're going to need some kind of adversarial computing where you want to deal with somebody and you can't trust them, but there's a mutual benefit if you can cooperate. And all of these cryptographic tools make this possible, but there's still a lot of very interesting work to do, and I think there's still a lot of low-hanging fruit for people like us. That concludes what I have to say.
Thank you, Maurice. Reminding everyone one more time that the meeting is being recorded. If you have questions, please raise your hand or type in the chat, and I will ask for you or prompt you to ask the question yourself. So do we have a question? I see Moshe is ready to go. So.
Yeah.
Oh no. Hi, Moshe.
Hey, so is anybody in this community thinking about?
On the other hand, they can maybe parallelize the PCT schedulers, right?
Yes, so that's what they do.
Is anybody's community thinking about the concept of declarative specifications?
That's not a question for me. That's a question for the community.
Well, I'm asking you from your knowledge of that community, has there been a topic there to think about declarative specification? As in fact, one phrase I heard the industry talk about declarative specification is designer intent, which is a way to bring the intent back into, even when people, when people write law, there are bugs in laws. And when they go to the courts, very often they think of what was the legislator's intent.
Yes, that's what distinguishes so-called smart contracts from real contracts. No, I've seen there's one smart contract language that I've used where you can have post conditions, and the post condition says no matter what just happened, you can't transfer more than $1,000 from my account. So there are ways. People have thought about this. I think it's still in very early form, but basically it takes the form of adding redundant constraints to your contract. Adding a sanity check that says that no matter what, you better not. If I authorize you to withdraw from my checking account, you better not be able to transfer my frequent flyer miles as well. But I think this is something that is still in its infancy, as far as I know.
I think Phil wants to ask a question next.
Well, I wanted to answer Moshe's question. He asked, is there work on declarative stuff going on? And the answer is yes. So a way back, Simon Peyton-Jones and Bakjan Eva, who's in finance, wrote a paper on how would you describe a contract in a declarative style? And since that thing at the turn of the millennium, there have been a large number of similar languages developed, and quite a few of those have been applied then to smart contracts or cryptography. So I work for a company called IOHK that has one of these, but other people have others as well. So there is definitely work in this area, and there's definitely quite a lot more to do. And then you also might want to think about how do you make your contracts themselves clearer. For instance, being a functional programming person, I would say, let's use functional programming. And a huge amount of the stuff in this area does use functional programming, in fact. So there's lots of interesting things to be done, lots of interesting overlap with the finance community, where banks also are using functional languages for the same reason. So there's lots of interesting stuff to discuss there. I will actually ask a question, which is picking up on something social that Maurice said, where he mentioned everybody thinks that they know how to design a programming language, which is absolutely true. And of course they don't. In the user interface world, there's this tradition that you don't just build your user interface, but you bring in an expert to review it. And wouldn't it be great if we could get a similar tradition established for programming languages? So if anybody wants to talk about how we could do that, I'd be very interested to do so.
There are companies that will come in and verify your smart contract, or at least audit it. That doesn't always work out well, but it's certainly better than nothing.
Yeah, a lot of that's just checking for the known bugs.
pretty much.
Okay, there is a question in the chat from Karim. He's asking if TLA plus can be used for smart contracts.
Absolutely can. In fact, I have a paper with my student who's going to, which is going to be in the next PODC, where we built a TLA plus specification for a two-party swap. I won't get into. It has some special properties that I won't get into. But if you want to verify a two-party swap, that's pretty good. If you want to do n-party swap, then you have the usual problem that you can do it for 2, 3. Once you get to 4, it starts getting kind of slow. But I think even though you're in a Byzantine environment, the contracts can sanitize their inputs to such a degree that it is possible to do finite state searches and verify that nobody is picking your pocket.
And Shankar, do you still want to ask your question?
Sure, yeah. So, building up on Moshe and Phil's comments, I was wondering, something like smart contracts, you don't have to take the code as the specification. You could actually have an independent proof system in which you record the transactions and indicate what is a legal transaction and what isn't. Have people considered doing that?
Well, I think this goes back to the question of whether you can have redundant statements. That as was pointed out earlier, there are a number of modern languages that are based on either functional languages. I'm working right now for a company that uses a Lisp-like language, although it's not entirely functional. So I think people have definitely thought about that. There's activity in these areas. I don't think the last word has been said on that.
Okay, great. So last call for comments or questions. We want to move to Tony. Okay, Leonard, you go last and then we move to Tony.
I was just a little bit surprised when Maurice mentioned breaking of abstraction boundaries and callbacks, and so as particularly new in this area. I was wondering, they're sort of at the heart of specters, for example, the breaking of abstraction boundaries as well, and double freeing and recursion with callbacks sort of has been plaguing us also for decades already. So I was wondering what is really so different in that setting.
Well, I think our field is mature enough that maybe we don't invent new things. We kind of recycle them and rediscover them. But this is something that is currently a common threat. As I mentioned, reentrancy attacks are at this point old news, and even a compiler the Solidity compiler will print out a warning saying, by the way, there may be a reentrancy attack here. But there are other attacks that are harder to detect and have the same kind of weird possibility. There are all kinds of attacks on things like gas. You have to pay for every instruction you execute. If you burn up your allotment, your program stops. And so if your adversary can trick you into burning up gas too quickly, then your program will halt in the middle, and you might not get your money back. There are many examples of abstraction breaking attacks that are different in flavor from the kinds of bugs that people look at mainstream programs look at. But again, I'm not saying that this is a new and unexplored area. There's a lot of activity in verifying smart contracts. I'm here as a consumer of smart contracts, saying you should drop what you're doing and help me out by making sure that these programs actually work.
Okay, so thank you very much for the nice talk. And please, everyone hang around, and maybe in the break after Tony's talk, we can still chat more with Maurice and about smart contracts. So Tony, if you're ready to go. You should unmute yourself.
Okay.
Great. And I think Tony does not really need any introduction, so I'll just let him get on with it.
Well, thank you, Maurice, for standing in for me over this rather frightening little gap in the proceedings. And thank you to the rest of you, and thank for listening to me on this occasion, which was to have been the first slot in the very first seminar of the Isaac Newton Institute program on Verified Software Initiative. Since I was personally involved in starting this initiative, I would like to recount some of the key events in its early origins. In 1968, I resigned from my first job working in the software department of a small British computer company. On unpacking one of the packing cases of papers that I brought with me, I discovered a copy of Bob Floyd's seminal paper on assigning meanings to programs. The formal technical content of my 1969 paper, published in the Communications of the JACM, an axiomatic basis of computer programming, at that time, I did decide to take program proving as the topic of my life's work, my life's research. I reasoned that this topic was unlikely to find application in industry until the date of my retirement from my professorship, which was scheduled 33 years later. Thus, there was no risk that my research would be overtaken by the vast sums of money that an industrial management can spend on a research project once it is recognized that the project is of value to the company. And then, against that flood of money, I would be forced to change my own topic of research, maybe at an age that would be difficult to make such a radical change later on. I'm glad to report that even now, I've never had to change the topic of my research. I am very happy to remain with verified software. On retirement in 1999, I was offered employment with a large US software manufacturer, namely Microsoft Research in Cambridge. I found when I visited the company in the production division that my 1969 prediction was correct. They were none of them using assertions or for their original purpose, but they were using them for program testing. And that is something which suddenly made me adopt program testing as one of the means by which, in practice, one can justify and take advantage of verification technology, same technology, just two different, same objectives, but just different methods of achieving them. In 2003, I was invited to submit a paper for the Journal of the JACM. This was on the special issue of the JACM was being published, calling for grand challenges for computing research in the 21st century.
Tony, sorry to interrupt. We seem to have lost your slides.
Oh, right.
If it matters that we see them.
No, not really.
Okay, then carry on.
Actually, that's just me. My VPN kicked me off. I'm coming back on. So I'll be there.
Hello, Shankar. Thank you very much for inviting me to give this initial talk. Hi, thank you. 2003. Oh, yes, the Journal of the ACM, special issue. The 2003 was the year of the announcement of the completion, the successful completion of an international grand challenge project for decoding the human genome. So I took that project as a model for deciding how what the features of a successful grand challenge project should be. And of course, with the genome project, the rest was history, except that application of this research is now a large part of our daily news. The title of our initiative was not recognized as a grand challenge by any of the national funding bodies. Every project had to be set up to obtain its funds separately. So the existence of this underlying project is actually not very widely known about. In 2005, the Zurich conference, Verified Software Theories, Tools and Experiments, attracted many world-leading computer scientists, just like this conference. And I think Jay Misra, if he's here, and certainly Shankar, were among our audience today. Does anybody else remember attending that conference, who's now here among the listeners? 103 listeners, I'm told. Perhaps this is not a question that one should ask in a Zoom meeting. After my experience of the technology, perhaps we won't ask to stretch it to its limits. The first 15-year phase of the Verified Software Initiative concluded last year. In moving to the second phase, I hope we will plan to discuss with the next generation of researchers, as well as with established researchers, a more ambitious and more integrated plan of research and development. That the final phase, obviously, we should think about, it will consist, I think, from the successive rollout of the technology, eventually to the entire programming profession, and to those who educate the professionals who will use it. Well, I will come on to stop talking about the ancient history, which our more elderly gentleman is inclined to do a little bit too long, and say what my present interests and research activities are. I'm working with three close colleagues. Bernhard Müller is an algebraist, and he has been making splendid progress on a common algebraic for the theory of programming, the theory of relativity, and formal linguistics. And now I remember it for the foundations of mathematics itself. And secondly, with Prakash Panankartan, whom I've just seen on the screen earlier today, earlier in my talk, and we hope to extend the basic foundations as find a foundation for quantum theory as well, which may prove valuable in understanding and using quantum computing and also perhaps AI. Now, with Peter O'Hearn, we're discussing the use of this basis in the design of an advanced programming toolset, perhaps an extension of the Infer toolset, which he has installed for his employer, Facebook. The toolset, the aim is, I think, must be that the toolset covers all phases of program development, from, I left out requirements analysis there is perhaps the most important starting point, through the formal specification, design that is correct by construction from the specification, code that is correct by proof, review, a successful review of the code before testing, which is common practice at least in Facebook, and I believe IBM, certainly in my rather old history I know of their programming methods. Finally, testing before delivery and testing after delivery, and the continuous evolution of a software product, but seemingly forever afterwards. Let's see now. And what about the future? Future hopes. Well, of course, I wouldn't be here if I didn't hope that the Isaac Newton Institute program on a verified software initiative will continue this initiative as a worldwide collaboration of theorists, tool builders, and I think now academics offering professional courses in software engineering. We must get the students who leave our undergraduate or who've taken professional courses in software engineering with an understanding of the use of even current industrial tool chains for program development. And finally, as a theorist, I hope that our discipline will be recognized as a mature branch of science, like physics or quantum theory, by researchers in these other well-respected and well-established scientific disciplines. Again, I'd like to say it's been a great privilege to address you in what would have been the opening event in the Newton Institute program. Thank you very much.
Thank you very much. If there are any questions for Tony, please raise your hand. While people are getting ready, let me start. I'm actually very interested in this last point that you made. Can you say a little more what it takes? Okay, first, do you think we are there or not to be recognized as a mature branch of science? And if we are not there, what does it take for us to actually get there?
Well, first of all, one hopes that the physicists and the formal linguists and the others will see and recognize that they share the foundations with us. We're all branches of something. And one of the characteristics of a mature branch of science is that it itself has many branches. And I believe that by investigating the logical structure of the axiomatic foundations of programming and programming language designs, we can show a rational basis for the division of our subject into branches. Branches tend to be, shall we say, evolved by natural selection at the present time. And I think, in fact, our subject is far easier in our subject than in most to delineate boundaries between different branches as soon as we all give up fighting each other about which one is best. And that was the objective of the first phase of the Verified Software Initiative 2.
Okay, there is a question in the chat, maybe for you, maybe if other people can also jump in. Is there going to be a retrospective of the first 15 years of the Grand Challenge program?
I believe that Jim Woodcock either has prepared or is preparing such a retrospective, at least in his area of interest, which was experiments. I think he has prepared one for experiments, and he may be extending that to the other two branches of our three-pronged attack.
Other questions or comments on this from participants?
Oh, where are we? It looks as though I have
So Tony, I'll ask one. In the past 15 years, has there been anything that one or two things that surprised you that pleasantly, and anything that you're disappointed that we didn't achieve?
I haven't thought about the disappointment, but what really surprised me was the appearance of separation logic. Fairly close to the beginning of the project. I thought when starting up the theory branch, I thought there would be two problems that we would have to deal with in the theory before we could get any widespread acceptance or use of a verification technology. One of them was object orientation, which is quite tough because the addresses are, the references are rather undisciplined in principle. Secondly, in concurrency. And so the introduction of concurrent separation logic by Peter O'Hearn, I thought solved both those problems at a stroke, and has proved to me a very great fillip to my own research anyway, on the theoretical side. What should we have done? I won't make anything up just at the moment, but it's an interesting question.
Do you have any thoughts on what you'd like to see in terms of automation?
One of the things I'd like to see is technique for heterogeneous programming, where a large application, like a cyber-physical system or indeed a great many standard commercial programs, are constructed of units made out of, which have been coded in different languages, special purpose languages. For example, spreadsheets is one of them. Functional languages where they are relevant and they are sufficient for a particular application area. Database searching, we all use some kind of database searcher. And all of these have to be built into an integrated system. In a cyber-physical system, more or less each component of the system is designed in hardware and in software by a different subcontractor. And they all use languages, maybe Simulink, maybe something else, which are just put together in the overall system by the prime contractor, who bears responsibility for ensuring that they are all consistent with each other and will perform safely and maybe even achieve certain economic and performance targets. So it's the people who take this central responsibility that are most keenly interested in what's in Jim Woodcock's field of endeavor, which is unifying theories of programming. So he's the one who told me about what his major client, commercial and industrial clients actually use his work in unifying theories of all the various heterogeneous components, software and hardware, that go into a cyber-physical system. Jim Woodcock again.
Okay, great. Just for everyone, now is the time that we can take a break, stretch your legs, and we reconvene in about 25 minutes to start with Anka's talk after the break. But of course, the Zoom is going to remain open. We are going to pause the recording, so you can kind of use this chance as discussing things. This is not going to be recorded. We are going to restart the recording at the beginning of Anka's talk again. Okay, welcome back. It's my pleasure to introduce Anka Scholl. Anka has been a professor at University of Bordeaux since 2006, and before that at University of Paris 7, and we seem to be mislisting her in our program. And her main research area is on the verification of distributed systems, and she has done a lot of great work on distributed synthesis and control, and on message sequence charts and communication models like that. So Anka, please.
Thank you. Thank you for the kind introduction. Thank you for the invitation. So I'm very happy to be here. So this is joint work with Igor Walukiewicz about negotiations, so about learning sound negotiations. Do you hear me well? Okay, thanks. So the talk is about a model for concurrent and distributed programs. And it starts actually with the observation that, I mean, as everybody knows, when you program, it's not the sweetest dream to have some concurrency around. And that's true when you write programs and also when you verify programs. So concurrency is hard to work with. Basically, simple questions like reachability are p-space hard, and you have lots of high side effects that when we write programs. And the purpose of the talk is to show you that still in this jungle of concurrent models, there is something that is tame, which is called negotiations, better sound negotiations. So this is a tractable model, and I will show you today a way how to learn these distributed models. So it's a tractable model also in the sense of verification. So several questions of verifications can be solved in polynomial time. But what is more surprising, even more surprising, is that learning is possible in polynomial time. Okay, so the model I'm going to talk about is based on shared memory. So as you know, when you have concurrency, you have two paradigms, communication on one side, shared memory on the other side. Communication already is very, very difficult because the models are usually too incomplete. We still have lots of nice theories there, like existential channel bounds, lossy channels, and so on. But I mean, it's clear that it's much, much more difficult to work with. Shared memory, on the other side, leads to finite state systems. So automatically obtain decidability, so for verification problems. But as known as verification is very costly. So why is verification costly? Because concurrency typically leads you to product of processes, so to state explosion. And you can, in the most concurrent models, simulate, for instance, the intersection of finite state automata, and you get immediately p-space lower bounds for the simplest verification problems. Okay, so I will start with a finite, so with a shared memory model for concurrent systems, which are Zielonka automata, which have a very rich theory. So there are very nice things to say about, and it's at the same time a very clear and clean model for concurrency. And I will take this as a starting point for negotiations. So what are Zielonka automata? So basically they consist of finite state processes that synchronize over shared actions. So you have a finite state automaton for each process, and each action has a fixed domain that involves a subset of processes. And such a shared action executes if all processes from the domain agree to execute it. So agree to execute it means that they are in a state that allows them individually to execute this shared action. So as I told you, so there's very rich theory behind, so the theory of Mazurkiewicz traces, and I mean that's probably the nicest model that we can work with in the shared memory area. However, the simplest questions here are already p-space complete, so like emptiness. So in 2013, Esparza and Desel, they came up with a simpler model that is actually a process-based versions or variant of what is known as workflow nets or business process models. A model that amounts to use actually free choice Petri nets. So for those of you who know the Petri net area. And in terms of Zielonka automata, so actually this model is quite powerful if you allow for non-determinism. So if you have non-determinism, then non-deterministic negotiations are equally expressive as Zielonka automata. However, if you restrict negotiations to be deterministic and sound, and I will tell you in a moment what soundness means here, then you get, so soundness is actually deadlock freeness, so you get deadlock free history oblivious Zielonka automata. So Zielonka automata where processes need to execute shared actions independently of exactly which is their state. So they just have to be in the situation of having to execute this shared action. So let me show you straightforward what a negotiation is, because I mean another nice point about negotiations is that this is a graphical model where you can see how processes evolve. So here you have a negotiations with 3 processes, P1, P2, P3, and there are here nodes. So the negotiation is basically a graph, a bit more complex graph, and there are outcomes. So nodes have outcomes. For instance, N0, the initial node has only one outcome A, but N4, for instance, has 2 outcomes, E and C. And each node has a domain. So each node involves a certain subset of processes. For instance, N7 has in its domain processes P2 and P3. And here you see the flow of the negotiation, so the transitions in the negotiation. And in some sense, why is it called negotiation? Because when 2 processes, several processes arrive at a node, for instance, let us take node N7. So processes P2 and P3 arrive at node N7, then they negotiate the next outcome. So they decide whether jointly they will execute outcome B or outcome H. With outcome B, they go to the final node. With outcome H, they get back to node N2. Okay, so You can see executions in negotiations by depicting configurations. So for instance, in the initial configuration, all processes are at the initial node, shown by these red points. And then if you continue, for instance, and execute A, B, C, G, so this means that process P1 is in a configuration at node N1, process P2 has executed A, B, and C, and so is now at node N7, and process P3 is at node N6. So you have configurations, and then you continue like this, and the goal in the negotiation is to start at the initial node and to end at a final node, so that all processes arrive at the final node. Okay, so I told you that we are interested here in deterministic negotiations. So what means determinism? It means simply that for every node and every outcome, every process in the node's domain has a unique next possible node. So for every step, if you execute a shared action, then the next configuration is uniquely defined. So that's the usual notion of determinism. What means soundness? Soundness means basically deadlock freeness. So it means that every run from the initial node can be extended in such a way that all processes arrive at the final nodes. For instance, you cannot have this red arrow from N4 to N8 that would allow process P2 to jump to the final node, letting process P3 starve in node N7, so that no possible continuation to node N8 is possible. Okay, so as promised, so we have a couple of nice verification results for sound deterministic negotiations, which show that the model is quite well behaved. First, checking soundness. Checking soundness is possible in non-deterministic logarithmic space. That may sound surprising because soundness is something about deadlock freeness, so it has something to do with configurations. And configurations, there are exponentially many because you have no fixed bound on the number of processes. Detecting race is also possible in p-time. Detecting races means that you want to know whether there is some reachable configuration in which two designated nodes appear both enabled, so where they can be executed. You can execute from these two nodes from each an outcome. This is also possible in p-time, although it talks about configurations. And more generally, there are several kinds of what we call Mazurkiewicz invariant data flow analysis, which is possible in p-time. For instance, computing minimal maximum time, execution time, or average cost, or for instance, intersection with trace closed finite automata. So if you take a negotiation and you have a finite automaton on the other side, and the finite automaton has the property of what we call diamonds, so the language of the finite automaton is Mazurkiewicz trace closed. In this case, we can solve this question in polynomial time. If the finite automaton is not trace closed, then this question becomes p-space complete immediately. So it matters that the automaton is trace closed. Okay, so what is the reason for all this surprisingly good behavior, in spite of the fact that we talk about configurations? So the reason is that there are two facets of sound negotiations. On one hand, we talk about configurations and we formulate the property of soundness in terms of configurations, so deadlock freedom. And on the other hand, we can express the same things by looking at passes in the graph of the negotiation and formulating properties by forbidden patterns. So let me give you an example for that. So to what amounts soundness for deterministic negotiations? It amounts to forbid patterns of the following form. So you forbid so-called forks. So a fork is something where you start at a node and then you arrive at another node where processes P and Q execute a joint outcome, go to two different nodes, then they progress independently, and both of them arrive to two different nodes where the domain of these two nodes include both processes P and Q. So this means that if, I mean, such a pattern, of course, leads to a deadlock, because if process P arrives at the left node and process Q at the right node, then they are blocked and they wait one on the other. The other, another pattern, similar pattern, is non-dominant, absence of non-dominant cycles. So what is a non-dominant cycle? So this is a cycle in the graph of the negotiation, which has the property that there is no node on the cycle in the domain of which all the processes that may occur in the cycle appear. So this is a non-dominant cycle, and this would lead also to deadlocks. And of course, we can check this in non-deterministic logarithmic space. So we can check the presence or absence of such patterns. So the problem is in n-log space. These sound deterministic negotiations have even more nice properties. So they're actually, one can decompose them in a nested fashion. And this decomposition, this nested decomposition, can be computed in polynomial time. So what does it mean in a nutshell, a nested decomposition? It means that you have at some step a sort of automaton. So you see here just a usual automaton, for instance, automaton with states, but with edges labeled by acyclic negotiations over the same set of processes. So at different steps of the nesting, you have different subsets of processes, and you have at each level, you have such an automaton where these acyclic negotiations involve the same set of processes. So in some sense, these processes start at some node, execute the acyclic negotiation, and meet again at the next node on the transition, and so on and so on. So these negotiations, some negotiations are basically a concurrent model where you know beforehand, in some sense, where processes will meet again. So it's not fixed, but there is something that, some common knowledge where these processes will meet again during the execution. So they have this synchronization mechanism that is rather strong. Okay. So let me go now over to the actual topic, so to learning negotiations. So the learning, kind of learning that we're interested in is active learning in Ungren style. So probably everybody knows Ungren's learning algorithm, but I will just recall very briefly. So you have a learner and a teacher. So the goal is to learn a DFA, a deterministic finite state automaton. So the learner has the possibility to ask equivalence queries to the teacher. So the learner has a candidate automaton and can ask, is this the automaton that accepts the same language as the automaton of the teacher? And if yes, then the game is over. If no, the teacher sends counterexamples. So counterexamples which are differentiating the two automata, A and B. Okay, so Ungren's algorithm works very well for deterministic finite state automata, and not only for deterministic finite state automata, actually. So it works well, in particular for deterministic finite state automata, because here we have a very, very strong property is that we have unique minimal automata to work with. So there is the Myhill-Nerode congruence, which makes this algorithm work, and the unique minimal DFA ensures, in some sense, the determination of the algorithm. What about applying this algorithm in a distributed setting? So this is particularly challenging because already in a distributed setting, it's hard to come up with canonical models. I mean, distributed models, Zielonka automata, whatsoever, they can have synchronization in weird ways. So having something canonical is very, very rare, because you can do things, if you have several processes, you can let one process work, whether the other one does nothing, or vice versa. And so it's no hope to have canonical models. Still, there are some results about active learning in the distributed setting. There's a recent paper on learning POMP set automata by these authors, but they learn restricted POMP set automata. So they are restricted in the sense that the POMP sets are restricted. And there is another paper also for learning communicating automata from message sequence charts. That one is also learning restricted communicating automata, because you impose some channel bounds which make them finite state. So then you basically learn finite state automata. Okay, so let me just recall very, very briefly what Almgreen's algorithm does in order to show how we modify it. So in Almgreen's algorithm for DFAs, you have states which correspond to words. So a set of words that are the states of the candidate automaton. And then you have some test words. And two words are equivalent with respect to the test set if, so two words UT, if UT and VT are either both in L or both outside L for every T in T. So you have some sort of, I mean, like in the Myhill-Nerod concurrence, but you work with the test set. And then what you basically do is to have a state's unique representative of these equivalence classes induced by the test set. So you never have two different words in Q which are equivalent with respect to the current T. And you get the transitions of the candidate automaton maintained by the learner by saying that you go from state U to state V with letter A if UA is equivalent T to the word V. So it's very simple, and this algorithm actually converges because you have an upper bound in the iterations of this algorithm which corresponds to the size of the minimal DFA of the language, and it's polynomial. It's a polynomial algorithm in the size of the minimal DFA and the length of the counterexamples sent by the teacher. Now, what about sound negotiations? How can we do this for sound negotiations? So the idea is rather simple, I would say. So it consists in looking at these sound negotiations by identifying local passes in the sound negotiation. So you have here in red a local path. So you see here action A executed by P3, followed by B executed by P2, then ECC executed by P2, and we finish with a B executed by P3. This is a local path. A local path is just a path in the graph leading from the initial node to the final node. So we are talking here about local paths and view them over an alphabet that corresponds to the product of outcomes and processes. And now something very, very nice, very cute happens. So if you take a sound deterministic negotiation and you look at the minimal automaton for the set of local passes of this negotiation, then from this minimal automaton, you can get in a very simple way a deterministic negotiation. So from automaton A, you get a deterministic negotiation N of A. This is very simple. So the states of the automaton will be the nodes of the negotiation, and you define in a very simple way also the transitions. And the nice thing is that the negotiation that you get is equivalent to N and is sound. So basically, this is a kind of minimization. Yeah? So you minimize the automaton for the that accepts the set of local passes of negotiation, and from this you recover the minimal negotiation, which moreover is sound, has all the good properties we want it to have. You get the minimal negotiation that is equivalent to the negotiation you started with. But this means also that since all these operations are in polynomial time, that we can do the following for learning. We can have as objective to learn the minimal automaton for the set of local passes of the negotiation. Okay, so how do we do this? So learner learners submits to teacher candidate negotiations. Candidate negotiations constructed from the current pair QT that it developed during the algorithm. If this candidate negotiation is not equivalent to the given negotiation, teacher sends to learner a counterexample, which is an execution. So we are not just applying Angluin to learn the automaton of the local passes, but we behave as if we send negotiations to the teacher and we get executions from the teacher back. And learner internally uses the counterexample to enlarge the automaton associated with Q and T. So the only point is that learner may ask now membership queries to the teacher about local passes. So we need this for enhancing enlarging the pair QT. Okay, so one may wonder here at this point how all this works in polynomial time, because teacher gives to learner executions. So executions are, I depicted here at the on the left side a counterexample, which is an execution in form of a partial order. So executions are partially ordered, and learner works with the local passes. So learner builds an automaton that is supposed to accept the local passes. So in such an execution, you may have exponentially many local passes. So how come that this works in polynomial time? Well, actually, we use here a strong property about coming from our Gaussian traces, which is that we can reason to some extent about only about projections of this execution on single processes. So if you look at the execution on the left, so the projection, for instance, on process P3 is formed by A, B, F, B. So this is the projection. And of course, there's only a polynomial number of projections. Now, we want to work with these projections in order to have the polynomial complexity. And now the main point arrives. So for some negotiations, so if a negotiation is sound, then if all projections of this if all projections of an execution belong to local passes of n, then the execution W is an execution of n. So being an execution of n depends only on the projections. However, the intermediate negotiations that the learner builds are not sound. They are not sound. They are very, very weird, as in Angluin's algorithm. So the intermediate automata are generally, they don't have any good structure. So they are not sound, but almost. So we ensure that we maintain a property, an additional property on top of Angluin's algorithm, which is called stability. So if the pair QT is stable with respect to all projections of counterexamples that we get, then these executions are still executions of the intermediate negotiation. Okay, so
Anka, sorry to interrupt. You're running out of time.
Since I'm running out of
question.
time, yes. So I'm almost at the end. So I will skip the stability, and I was almost at the end. So the stability is just on top of Angluin, so it's something that doesn't hurt. So it's still polynomial. So it shows that sound determinist negotiations can be learned in p-time. It shows that we can check equivalence of sound determinist negotiations in polynomial time. And this also shows also that sound determinist negotiations can be minimized in p-time. And yeah, so let me go over to the conclusion that raises some questions. So something which is still open is how we can learn sound negotiations using executions for membership queries instead of local passes. So this is something that we are working on right now. And the second question is maybe more importantly, I mean, there's a lot of structure in sound deterministic negotiations, and it would be nice to identify which are the most important features of this structure. So how can we use these features for Zilonka automata in order to hope that we can learn or minimize or get polynomial time algorithms for more complex models than negotiations? So this was my conclusion, and thank you for attention. Sorry for being too long.
Thank you. We have maybe time for one quick question. And if you don't catch Anka and you had a question, you can feel free to continue in the chat, and I'm sure she will see the questions and answer them. Okay, it seems like there are no immediate takers on the question. So Mehmet, you're next. Do you want to start sharing your screen to see that everything is working properly?
All right. So you see something?
Yes.
So let me try to put the full screen. Or if it works, I don't know. Let me see. Oh, no. Do you see this? Is it full screen?
We see a black screen. At least that's what I see.
Okay. So I don't know then. Okay, let's see.
Maybe one more time. Seemed to be like a refresh issue.
Okay, let me try. What about now?
No, same problem still, just a black screen.
Okay.
Is it possible you've shared just one window and it's not the right one?
So, I think it's...
So this is fine. Yeah, why don't you proceed with this?
Okay, so then let's continue like this, okay?
Okay, so let me just quickly do. It's my pleasure to introduce Ahmed Bouajani. He is at the University of Paris, a professor there, and he works in algorithmic verification with a particular focus in verification of concurrent and distributed systems. Please.
Thank you very much for the introduction. So I am going to talk about, in general, program verification and their weak consistency. And this is based on a joint work with many great people who are listed there, but the list is not exhaustive. So we are interested in this work, I mean, in what I am going to present, the verification of applications. And these applications, as the picture is showing, it will receive a number of queries sent in a parallel way by several clients, and this will trigger, the several threads and parallel tasks that will run, and will call, operations like read and write that access some storage systems or a memory. So, and they of course have a concurrent access to this structure. So the application must guarantee some functional specification to the client, and in the same time, it assumes some memory model that abstracts the way that this system is working. So a consistency model, basically, it will define how the updates are made visible to each of the threads. So for instance, if we take the standard, let's say, interleaving model called sequential consistency, their writes are supposed to be immediately visible to all threads. So, and this offers the highest consistency guarantee, which is very desirable abstraction to the application writers. And in the same time, it's of course hard to ensure in the same time if we in the same time we want to also provide some high performance. So usually implementers of storage systems or memories will ensure something weaker than this model that offers strong consistency. And this is why people consider relaxed consistency models. So in these models in general, the set of visible updates can be different from a thread to another one. So at some given point in time, so they will not be aware of the same updates. And when these updates will become visible to them, they might be visible in some different order. So, and this of course may create a lot of complex behaviors, and application writers have, to deal with that. So for instance, total store ordering, which is in some sense, let's say, the strongest relaxed memory model, there only writes are allowed to be, so the writes are allowed to be delayed, but they are, when they become visible to other threads, they will become visible simultaneously to all threads in the same time. So if we model this abstractly, operationally with some operational model, basically it means that we will have to introduce some kind of store buffers where writes are going to wait pending there for some moment before they will be committed to the memory. And this means that in the meantime, so reads may overtake them. And of course, this means also that reads are going to be maybe faster. So the access to the memory with reads will be faster, but it will probably provide old values of that are not yet up to date, because some of the writes are still pending in buffers and not yet visible to all the processes. All right, so of course this creates a lot of issues. In many cases, this kind of relaxation can be okay for some applications, because the requirements from this application, I mean, the specification that has to satisfy is not affected by this kind of behaviors. But in some other case, this can be problematic. And the programmer must insert fences in the right places to ensure correction of its application, of his application or she's application. So, but on the other hand, fences, of course, they may harm performances. So excessive use of fences can be harmful in terms of performances. And this is why somehow it's hard to ensure in the same time correctness and also some optimal performances. So then one needs to have automated methods for verification of correctness under weak consistency models. And those models, as we have seen, they may generate complex behaviors. And also, we need also some procedures for fence insertion and optimization. All right, so here in this talk, I will talk about some of the verification problems. So the basic one is, of course, correctness under relaxed memory models. Given a program and some specification, and given a consistency model, we need to check if the semantics, or let's say the set of visible behaviors of a program under this memory model M, are all correct with respect to the specification. So that's one well-known problem. Of course, here the problem is to take into account this memory model. Another interesting problem is so-called robustness against these relaxed memory models, which means that now we are given two models, M1 and M2, and let's say that M1 is weaker than M2, and we want to check that actually this relaxation doesn't introduce extra visible behaviors of the program. So this means that the set of visible behaviors of the program running on top of M1 is actually a subset of the set of behaviors of the same program under M2. So in some sense, you take the semantics of program under the strong model as a specification. All right, so we'll see that this problem can be useful because in some sense it gives you a property that is independent somehow from of a given specification, but sometimes it's about a class of specifications. So, and if this property holds, then if you know that the property holds already, let's say that some specification is correct. I mean, the program is correct with respect, to some specification under the strong model, then you can preserve in some sense that property for the weak memory model. All right, so let's start by the basic problem, which is a reachability problem, which allows you to check, for instance, basic safety problems. So here we have to deal with complex order constraints. And as you have seen, for instance, in the model of TSO, we have these store buffers. And in principle, these buffers are unbounded. So this means that if you look at the state space now of the program under these models, it's infinite. Even if actually originally under SC, this program is finite state. So now this raised the questions, what is the decidable, is this problem still decidable for a given model? And what would be the complexity? So the approach that we adopt in general to attack this problem is to ask whether we can turn this model, I mean, the formal operational model of this, the program into some well-structured system. So this is to use the nice theory of well-structured systems, which is a well-known theory allowing to derive decidability results for reachability problems for infinite state systems. The basic ingredients is that you have to come with a well quasi-ordering. So on the set of configurations, so this is an order where you cannot have some infinite descending let's say chain without finding two comparable elements, and you cannot right, and then you have this important property, which is monotonicity. And monotonicity basically means that this order, when you consider that relation on the set of configurations, it's actually a simulation relation, which means that if you do a transition from some configuration, now if you start from a configuration that is bigger in this order, so you can again do this transition and reach another configuration that is bigger than the previous one. So, and now, and there's some also effectiveness assumptions. You can prove the basic nice theorem in this theory is that you can compute the set of predecessors effectively. So if you start from an apport closed set with respect to this order, so this set can be effectively computable. And this is what is useful for checking state reachability in general. And this will be the, let's say, the framework that we are trying to use in this, to solve this problem in this case. So let's see, how do we do that, for instance, for T. So here we have this unbounded FIFO queues. So in this theory of well quasi-ordering, so we have this well quasi-order, which is the subword relation. So now, of course, if we ask ourselves whether this model of TSO would be monotonic, of course, no, because if I, let's say, I forget about, let's say, some operation in the buffer, so it will lead me to some behaviors that were not possible under the original semantics of T. So I cannot just forget about some write operation, okay? So this would allow some read operations that were not possible before, and this is not a sound simulation of the semantics. So we have to do something else. So now we have to transform this model into an equivalent one in terms of reachability, but which is still has this monotonicity property. So for that, one idea is to use what we call store snapshots. So in fact, instead of storing writes, as in the original semantics, let's say that now we store the whole snapshot, I mean, which is the whole contents of the memory. Right. So for instance, in this example, you see, so originally we started from M0, which is the original memory. And now, as you see in the picture, so we don't have now any one single memory, but one memory per process. And this process, actually, they should agree on an order of how this memory is going to be updated. All right. So for instance, here they agreed that first, let's say this PN will do some operation and we get this contains M1 from M0. And then we will get M2 and then M3. And let's say that this was done by P1, by operations by P1, and then M4. This means that now each of these processes, either he will perform a write and he will insert it there, or he will guess that his partner is going to do this writes and he will insert it. But they have to agree on that. So they have to synchronize about this sequence. But now, of course, they can be at some point in time at different positions in the history somehow. So for instance, here Pn is very delayed. He's still on his view of the original memory, and he has not yet seen all the sequence, whereas P1 is a bit in advance. He has already seen M1 and he moved to and now he moved to M2, and this is his current view of the memory, and he has still something pending there, right? So this is now actually one can check that now if I can just miss one of these views, it's still monotonic in the sense that I can miss, if I miss one, it's just, it's a valid computation because it's like, things were too fast for me and I missed actually one of these snapshots. So you can show that this model will simulate exactly the original one, and this one is monotonic. Now, actually, here one can see that's all right here. So this model theoretically is nice, but one has to store the whole memory contents, so which is maybe not very practical. So another alternative semantics, and this is is that actually we can reverse our view. Instead of using in the original TSO model write buffers, we use load buffers. So now the semantics goes the other way around. So when you do a write, this write goes immediately to the memory. And then the flow of information goes from the memory to the processes. So, and actually this memory is sending the read values that these processes may use, right? And so now, and actually, so what happens is that in fact, these processes will read again old values, but this is correspond exactly to this semantics of delaying somehow the write. So in some sense, when you read maybe old values because these reads have overtaken some other writes. So actually you can show that this kind of dual semantics is equivalent to the original one. And the advantage of this is that you can just skip some reads and doesn't harm. And this is magically monotonic. So this way we can show that this TSO is we can come with the monotonic well-structured system, and this shows that the reachability is decidable. Unfortunately, now from the theoretical point of view, the complexity would be high because this type of models with unbounded queues, so even if they are monotonic, so they are decidable in that case, but with the non-primitive recursive complexity. So more recently, we have considered the case of persistent memories. So as you know, I mean, if we have volatile memories, so if you have crashes, then the whole contents will be lost. So then to achieve persistency, you need to have some external storage, like a hard disk or something. So recently, some kind of architectures have been developed called non-volatile random access memories. They offer somehow the advantages of both things, while in the same time you have direct access and fast access to the memory, and you have also low latency for access memory. So now to reason about this new architectures, you have to consider both the consistency model as we have seen before, but now we have also a persistency model that determine the order in which the updates or the writes that or the values that are in the memory will be persisted. all right? And what are the visible states after the recovery, right? So, and the problem, of course, here is that, again, for reasons like performances, the writes will not necessarily persist in the consistency model order. So they will not respect, for instance, for T, so they will not respect the program orders. So they can have different orders. And also you have a lot of, now you have to deal with many types of fences. Fences that that are related to consistency, but also fences related to persistency that in some sense allow you to enforce some order of persistency. And of course, the semantics of these fences can be quite complex because they have many complex interactions with other operations like writes and so on. So recently, let's say 2 years ago, Azaliya Ra'd and her colleagues, they developed the first operational model, formal model for this architecture for x86 TESO. And so, of course, here I'm not going to describe it in details, just to show you these pictures. It shows you that basically you have, if you look at on the top, you have the original model TESO, and here you see, you can see that there is something new that has been added, which is this persistency stage that's in some sense encode how the persistency is going to do. And actually you have additional buffers, but you have many other features that make this model quite complex. So first of all, these buffers are not necessarily FIFO. So reorderings can happen in this buffer in allowing, following different kind of policies. And in these buffers, not only they contain writes, but they can also, contain fences and barriers because they have to respect some kind of orders that needs to be preserved. And also reads are not local, they can be from any stage and so on. So all this makes this model quite complex and very hard to transform into this framework of well-structured systems. But so recently in 2021, we came with an equivalent model that has this property of well-structuredness. And here, as you can see from the picture, is that basically we separate the TESO stage, which is quite similar to TESO with some additional features. And there is another stage which is which handles this the persistency model somehow. Of course, here, I mean, there are many technical details. I'm not going to go to these details, but just to give you some flavors, is that here, for instance, this locality of reads, for that we need to introduce some intermediary memory, and that is the TESO stage that you can see on the left. And also we had to transform these buffers from to FIFO buffers, and this transformation is quite complex and subtle. So actually, for the TESO stage, the one that is on the left, we use load buffers plus some finite state protocol that allows us to simulate an unbounded number of persistency fence that can be traveling in this stage using only a finite memory. And this is actually the hard part of the proof for this model, is to show that this can be done in this way by separating these issues and having this composition of load buffers with this finite state protocol. And also for the persistency stage, we use also FIFO buffers, a system actually of buffers to preserve the orders that are imposed by the semantics. But actually, we need for that to use the snapshot semantics. Actually, we are working now on simplifying this stage to get rid of this snapshot semantics. But yeah, but now by doing that, we reach we obtain a model that has this property of well-structuredness, and which shows the decidability of this model. All right, so if I have just a little time, I can just talk about this robustness quickly. So
Ahmed, you can take more time, but then you're cutting into your question time, so your choice.
Okay, so just 2 minutes then, sorry. So just robustness, I just want to define it by saying that, okay, state robustness means that, for instance, for TSO, is that, okay, either you consider states, and this would say that the state of fishable states under TSO is the same as the one under SC, but this notion is actually decidable as, because we can use the decidability of reachability, but it will be expensive. We can show that it's as expensive as reachability. Now, what is interesting is that you can strengthen a bit the notion of robustness and take something called trace robustness, where you use the notion of happened before relation, and you can now define this notion of robustness based on that. And what is interesting on that is that we can show that for this notion, we can reduce the verification problem of trace robustness to a state reachability under SC, which is much more cheap than the reachability under TSO. So that's the basic fact. So the reductions uses a notion of borderline violations that we need to track using some instrumentation of the original program, and the whole idea is to make this instrumentation finite and of reduced size, so that we can get a p-space completeness, this complexity for this problem. All right, and just to also to tell you that these notions are not specific to hardware models, but they can also be used in a similar way in the framework of distributed systems. For instance, recently these notions of robustness, we have studied them in the case of transactional consistency models, and we have, for instance, investigated the robustness, against, relaxed models like snapshot isolation, causal consistency relatively to the strong consistency model serializability, and also between weak memory models themselves. I mean, for instance, you can check whether your application is robust against SCC relatively to snapshot isolation. All right, just for the conclusion, so the verification of under weak memory models is hard in general. It can be highly complex or even indecidable. So, I mean, there are other cases that I have not shown here where we can prove indecidability. But trace robustness is an interesting notion because it gives a good approximation of, for states robustness, and it allows to lower the complexity for verification. And actually, all these techniques can be used for fence insertion, and actually also many approximate algorithms can be derived from these techniques. And actually, there is a lot of work on this area with many other people. Many of them actually are here in this audience concerning various techniques that are efficient for verifying, this type of concurrent and distributed systems. Now, there are many still open problems like how to find the generic specification and verification framework that can be used for reasoning about these models. Still, because for the moment, only a few models have been investigated, and each time one has to look at very complex details and so on. It would be nice also to have something that allows to have a methodology for tackling these problems. All right, so I thank you very much for your attention, and sorry for the delay.
Thank you, Ahmed, for a great talk. We have time for maybe one quick question if anyone wants to jump in. Let me ask one quick one myself. So when this story started, at least when I remember it, data race freedom was this kind of simple way for a programmer to decide that the weakness of the memory model doesn't matter. If you're data race free, you can ignore the weak memory model. And then you talked about the two other notions, robustness, and then this stronger notion of robustness that sort of close the gap. So data race freedom is very easy for the programmer to imagine. I mean, maybe not super trivial to check, but it's kind of close to programmer understanding. Is there some, is the strong robustness notion the same? If not, is there something between the two ends that could be something both easy to verify and easy to kind of understand at the high level reasoning of the programmer?
Right. I mean, these two notions, of course, they are not the same. In some sense, robustness is what you would like to have. And the data race freeness, in some sense, will be, in some sense, guarantee robustness, but you may have, you know, programs where you have data races, but still they are robust. So, all right. So, whether it's easy for a programmer to recognize what is robust and what is not, that's an interesting question. Not easy, because this is more a semantical notion than a syntactical one. So I agree that this is in some sense, but the thing is that algorithmically, the complexity is not higher. So, all right, so the notion of robustness, in some sense, it tells you that with the, let's say, the same complexity, you can let's say, admit programs that are more programs than just the data race free ones. Right. So, but it's not clear how do you characterize it syntactically, or so how do you find something in the middle? Well, yeah, so there are maybe some ways, of course, of how do you program in a let's say in a good way, but you are but not necessarily data race in a data race free manner. So we have not looked at what this kind of things. This reminds me in another context. We were looking at asynchronous programs. So when you have, let's say, I mean, you can use some similar ideas. So for instance, when you have asynchronous programs, so the semantics, of course, is parallel, but what we consider as maybe a well-defined program is the one that has, an equivalent semantics if you consider that, let's say, for instance, the calls of or creation of threads are similar to procedure calls, I mean, roughly speaking. So which means that, okay, if you deploy this asynchronous program on only one thread, it will show the same semantics. So in some sense, you can sequentialize it. So how do you obtain this property just syntactically? So there are ways. But those ways, again, they will be too restrictive with respect to this. But you could define this kind of things, which are not just data race freeness, but just how do you put these calls where in the program and so on. So that gives you some conditions that guarantee this kind of sequentialization.
Okay, thank you. So I see Moshe is ready. Rupak, why don't you start sharing the screen, and maybe Moshe can ask very quickly and Ahmed can answer very quickly while you're testing your screen.
Go ahead. Go ahead.
Oh, you don't want to ask a question?
No, not this time.
Okay. All right.
Okay, thank you.
Okay. So thank you very much, Ahmed. It's my pleasure to introduce Rupak Majumdar. He is a scientific director at Max Planck Institute for Software Systems in Kaiserslautern. His interests are in the theory and application of formal methods. Please.
Thank you. I'm going to talk about random testing. And I know that this is a workshop on verification and sound analysis, but hopefully I will try to show you that there is some there are some things that our community, our formal methods community can do in combination with random testing. And here's the thing, I work in formal methods. I like to prove things. I like to prove soundness guarantees. But despite many of these formal approaches that we have developed over the years, most practitioners test their code. And moreover, a lot of these tests are essentially providing random inputs to the system and seeing what happens. And at this point, our judgment would say, well, it would be really unlucky if this random choice of inputs will find anything interesting. But despite our best judgment, it turns out that testing is often surprisingly effective in finding bugs. And what I want to explore in this talk a little bit.
Larger screen.
Oh, you cannot see this?
We can see it, but it's somehow a very kind of narrow one with a smaller square in the middle. Well, it's not that small, but relatively speaking.
Okay, so this is something that I'm not sure about. Let me
go to design. Slide size. Okay.
Okay, let us see this. Is this any better?
A little better.
Yeah.
Okay. Unfortunately.
Why don't you just full screen the raw PowerPoint if you, that was better actually. If you can just full screen this.
Sorry, let me just try one more time and then perhaps I will. Is this any better? Or okay,
just keep going, keep going.
Okay, yeah. So the question that we would try to address is whether we can explain theoretically this effectiveness of software testing, random testing, and if random testing is not effective in a particular scenario, can we do better? And at this point, I would like to say that we have experience as computer scientists in dealing with randomness, and this is through the field of randomized algorithms. So a way of thinking about my talk is, can we treat random testing as the design and analysis problem for randomized algorithms? And what I will try to do is that I will try to show two instances. The first one is an existing testing algorithm that does very well in practice. And we will try to explain why we expect it to work well in practice. And the second one is a new random testing algorithm that will be inspired by the failure of naive random testing. And we will show that how just taking the lens of randomized algorithm design can help us get a better random testing algorithm. So let me start with the first. So there is a rather informal view in the software testing world, which says given the right notion of depth, every bug is shallow. So sometimes this is called the small model hypothesis, but usually this is a more rule of thumb rather than a mathematical statement. Now, what we try to do is we try to mathematize this intuition. And what we shall try to do is that this notion of depth will be covered by certain classes of combinatorial structures. And the shallowness will be characterized by certain algorithmic bounds on the families of these combinatorial structures that we shall define. But before we go to a very particular instance, what I'm going to do is that I'll set up the problem of testing and coverage in a slightly general way. So I will think of a testing problem as you're given a space of coverage goals, and you're given a space of tests. And the goal of testing is to be able to run enough tests so that every one of your coverage goals is met. So for example, unfortunately, I think my attempts to change the aspect ratio must have maybe I just continue. So some of the graphics, unfortunately, may not work so well because I think it got scaled to various options.
There's a hypothesis that you're sharing your whole screen rather than just the specific window.
Let me try to do that. Maybe I stop sharing and share.
Stop sharing and then share only the PowerPoint.
I think PowerPoint did something, but it probably doesn't matter. Let me just continue. So essentially what we're going to do is we have a space of coverage goals and we have a space of tests. And the goal is to find find enough tests to cover all the coverage goals. So for example, you pick this test on the right-hand side, it covers a possible, a set of coverage goals. You pick another one, it covers something else. You pick a number of tests and you stop when all your coverage goals are met. Okay. Now, a covering family of tests. So this is, how many tests should you run before you stop and say that, well, you have tested enough. Let me call this a covering family of tests. And this is relative to one of these coverage goals. So it's a set of tests that cover all your goals. And in a sense, if this family is small, then you have more efficient testing, right? So you have a small number of tests that already are good enough to cover all your coverage goals. Now, we shall be silent on how you pick these coverage goals, but the assumption is that there is some empirical correlation between your coverage goals and the bugs that you're trying to catch. Now, in random testing, it's more or less the same picture, but you can think of a probability space defined over the set of tests. And essentially, at each step, you pick one of these tests at random independently, and you see what coverage you get after a certain number of tests. And the question that we want to ask is, under what circumstances is a random testing procedure going to find a small covering family? So let's think about this in a slightly different way. So imagine that you have a particular coverage goal that you have in mind. This is this blue dot on the left-hand side. So let's say we fix this goal. Then we can ask the question, if I pick a random test, what is the probability that this random test covers this fixed goal? And imagine that somehow you figure out a lower bound on this probability. So you have a lower bound on the probability that this red test picked randomly over the space of tests covers a fixed goal. And let us say this lower bound is P. It turns out that just by using this lower bound, you can prove the following theorem. So if you have a set of goals G and you have this lower bound, then there always exists a covering family whose size grows inversely proportional to this probability and logarithmically with the size of the number of goals, logarithmically with the number of goals. Now, this uses the probabilistic method from combinatorics. So usually these theorems give the existence of a family, but these are not constructive. I won't be able to give you a particular covering family very easily in all cases. But I know one exists. And if you look at the proof of these probabilistic, these arguments by probabilistic method, they actually say more. It just says by repeated random sampling, this method of random testing is overwhelmingly likely to find a small covering family, a family, let us say, that's twice this optimal size of 1 by P times log G. Now, if you can imagine that the number of goals grows much more quickly. So, the log G essentially says that instead of an exponential growth in the number of tests, you can often get away with a polynomial growth. Okay. And of course, this there is a term 1 by p that talks about the probability of a random test covering a goal. So all that is very nice. Let's try to see what happens in a very specific case if we want to apply this theorem. So again, we have the coverage goals, the tests, and we would like to prove that random testing will work well. So we have to answer what are the coverage goals, what are the tests, and what is the probability space over which these tests are chosen, and can we bound this lower bound on the probability. And I will pick a very specific case where I will show that this can be done. And this is about a tool called JACM. This is a tool designed by Kyle Kingsbury. And this tool essentially does black box random testing of distributed systems by randomly inserting network partition faults, then healing the network and seeing what happens. Now, there's a very famous result in distributed systems that says, well, if you have partition tolerance, then each system must either give up consistency or availability. And essentially, JACM just tries to do this and sees what happens. And in this way, it actually finds a huge number of bugs in production distributed systems. And we wanted to say, can we explain the effectiveness of JACM? So the particular kind of coverage goal we'll have in mind is something we call splitting families. So you can imagine that you have a network. Each node corresponds to a node in the distributed system. And a network partition is somehow splitting this network into a partition of sets of nodes. And we'll say that one of these partitions splits a specific set S of k elements if each of these elements belong to different sets of the partition. And a set of partitions is a splitting family if for every k subset of nodes, there is a partition that splits it. You should think of each partition as a test. This is a test that introduces a specific network partition and sees what happens. And the coverage goal is that if I give you, let us say, a 3-tuple of nodes, you should have a test where these 3 tuples, these 3 nodes cannot communicate with each other. And the reason we want to, so this is an example. And the reason we want to pick this coverage goal is that many instances, many examples of bugs that JACM finds can be explained by saying, oh, look, there is a leader here and a leader there, and they cannot communicate with each other, and that's the source of the bug. Okay, so we have said that the coverage goal is case splitting. We have said that the tests are randomly sampled partitions. Can we bound this probability that a random test covers a goal? And our result from a couple of years ago is that, yes, with some combinatorics, you can show that the probability that a random partition splits a specific set S is a function that depends on k, that is the k splitting in your coverage goal, but not on n, the number of nodes in the network. Now, in practice, you could imagine that k to be rather small. You could imagine that k is something like 2 or 3, right? I want a bisection of the nodes or a trisection of all the nodes. And if you now apply this result to the general coverage result, you get that there is a k-splitting family whose size grows with some exponential function of k, but k, think of it as a small parameter, but only logarithmically with the number of nodes in the network. And at this point, if you go and plug in the numbers that are reasonable for the test that JACM runs, you see that just a random sampling of these network partitions should be able to give you a k-splitting family with only a small reasonable number of tests. And this is one way of saying why this kind of random testing of network partitions is likely to work well in this scenario. So let me move on to the second case. And in this case, we shall start with a random testing algorithm that does not work so well. And we shall come up with a new random testing algorithm that has a certain nicer guarantee. And I will motivate this by an example. So imagine that you have 3 processes that are sending each other messages, and the messages are asynchronous. And let us say that this system is buggy if the flush message executes before the log message. Now, because the system is distributed, and the messages are asynchronous, it is possible that the log message is delayed to beyond the flush message. And this is what we are trying to find. Now I can think of this system as essentially a partially ordered set of events, right? So initially there is a request event that comes in that generates two events, the log and the terminate, and there is no dependency on these two messages. The terminate message causes a flush message to happen, and flush causes flushed. Now, if you just use a naive random scheduler, what that scheduler is going to do is at each point, it's going to look at all the outstanding messages in the system. It's going to pick one at random and execute it. In this case, the random scheduler finds this bug with probability 1/4, but just adding many more messages between the terminate and the flush, you can get this probability of success exponentially small. And this is because at each point, the random scheduler is deciding whether I should execute log or something from the right. And if you have k things on the right, then log is delayed to after flush only with probability 1/2 to the k. And what we shall show is that we can define another algorithm that defines this bug with probability 1/2, even when you introduce new messages between terminate and flush. And this is the basis of a tool that we have developed called HitMC. And this is a tool that is a black box tester for message ordering bugs in distributed systems. And we have applied this to a bunch of production systems and found known and new issues. Now, again, the first point that we get here is what is the sample space? Or what is the coverage goal that we're trying to get? And the coverage goal is something that we call hitting families. So if I give you a partially ordered set of events, we say that a schedule or a linearization of the partially ordered set hits a particular D tuple of events if it executes the events in the order E1 happens before E2, happens before E3, happens before E sub D. And a family of schedules, a family of tests, is D-hitting if for every D tuple of events, there is a schedule in F that hits this event. That is, it orders these events in this particular order. The reason we choose D-hitting is that empirically, many bugs in asynchronous programs can be explained by the ordering of between a small number of events. Right? So this has, in various places, been called the bug depth of a distributed system bug or a concurrent bug. A different way of thinking about it is that essentially this parameter D kind of structures the search space by looking at small number of interactions first, and then successively including more and more orderings between events. Okay. And this last picture at the bottom shows a known bug in the Paxos implementation in Cassandra that uses, I think, about 6 or 7 events that have to happen in a particular order. Now, there's actually a very nice connection between our notion of hitting families and what is called the order dimension of a partially ordered set. So for a partially ordered set, the order dimension is the number of linearizations whose intersection is the poset. So it's a very well-studied concept. And it turns out this order dimension is really a special case when D equals 1 of a hitting family. And we essentially generalize this notion of order dimension with this parameter D. Now, the case that we look at is something called the online order dimension. And this is because when you run a system, it's not like you're given the poset up front, but you see the poset one element at a time in an upgrowing manner. You see the poset online as more and more messages are executed in the system. Now, the underlying algorithm that we get is a very simple randomized algorithm. It maintains an online chain partition of this poset of message events that we see as we run the system. It assigns a random priority to each of these chains, and it always executes enabled events from the highest priority chain. And in addition, at D-1 random points in the execution, we decrease the priority of the current executing chain. So the algorithm is very simple. It turns out the analysis of, just on this example that I showed you before, it turns out that the chain partition essentially has a left chain and a right chain, and it only picks the ordering between these two chains at random. So with probability 1/2, it picks the one on the right to execute before the one on the left. So the bug is found with probability 1/2. And this is no matter how long this chain on the right is. Now, it turns out that this very simple algorithm has a very nice guarantee. It tells you that each D tuple is sampled with a probability that, that grows with the width of the unknown poset. Of course, the algorithm doesn't even need to know the width of the poset. The width you can think about is a measure of how concurrent is the system. And it only grows as a polynomial function of n, when n is the number of events in the poset, and d is the small constant that has to do with the d-hitting family. In contrast, if you just pick random testing, then you would get a similar result where the probability will be essentially 1 by some exponential function of n. So essentially, we are restricting the sample space, and we're designing an algorithm to more effectively bias the search towards this restricted sample space. The correctness argument actually uses some rather difficult combinatorial arguments, mostly from this online dimension theory from lattice theory. But the final algorithm is very simple to describe and also to implement. Now, so far, we have looked at these algorithms where we think of the underlying system being tested as a complete black box. We just look at this poset of messages. But it turns out that you can do even better if you have some understanding of the algorithm that you're testing. So for example, many consensus algorithms implement what is called a round abstraction, or implement a model called communication closure. In this case, you can show that every asynchronous execution of the system is equivalent to a much simpler one. It's a lossy synchronous one where messages are either delivered within the same round or are just lost forever. And this allows us to even further reduce the sample space. And moreover, in some hand-wavy way, it gives us error traces that I would argue are more easy to understand and debug. Right? So I have drawn this pictorially of the same bug in Cassandra, the first one with a general asynchronous model of computation, and the second one that uses the fact that we are looking at these communication closed systems, so we only need to look at messages of a particular kind. So I'm almost at the end of the talk. So essentially, I started with this hand-wavy notion of, the notion of depth and shallowness of a bug. And essentially, I've given two examples, one where we can use probabilistic approaches to justify why an algorithm works well. And in the other, where we have designed a new algorithm that essentially samples a smaller sample space more effectively. So I will stop here. Let me say that this is joint work with a lot of people, but especially with my former student, Philip, and former postdoc, Burju. And let me stop here with this slide, which could be a starting point for further discussion. Thank you.
Thanks, Rubak. Moshe, please.
So you made a probabilistic argument that there is a small family of tests that will cover, with high probability, will cover the bugs. But I expected another result, because when we sample, we don't know that we are going to hit this particular family. So I was expecting some result that will say, if you want to have to include a testing family with probability, with certain probability, then you need to do so many tests. And you didn't have such result. And I think you need such result in order to tell us how many tests do I really need to do when I sample at random.
Yeah, so this is essentially what our result states, right? It kind of gives me, given the set of tests, given the coverage goal, we will tell you, you need to run so many tests, each picked uniformly at random from your set of tests. And this will give you a probability of, let's say, 1 minus epsilon, that you have sampled a hitting, a covering family.
But then epsilon should appear in the bound, and I didn't see epsilon in the bound.
No. So the way the epsilon is, well, okay. So what we do is the following, right? So we say that there is a covering family of a particular size, and then we use Markov's bound to say that, okay, if you run tests that are twice as many, then with probability at least half you get a covering family. If you run tests that are k times as much, then with probability 1 by 2 to the k, 1 minus 1 by 2 to the k, you are guaranteed to get a hitting covering family. So we get the results of your kind, but we state it in a slightly different way, in the sense that the probabilistic argument says, here is the size of your covering family. And a covering family you can get with high probability by purely sampling independently.
Okay, thank you.
Any other questions? Okay, I'll ask a quick one myself. If I understood correctly what the definition of the deheating family is, it seems to me that two different choices of deheating families are not equal, in a sense that one could basically correspond to a trace that corresponds to precisely one linear extension, as opposed to another one that can correspond to exponentially many linear extensions, depending on how you choose your choice of this goes before that, one ordering. So yes. Isn't there like a disconnect between these two kind of extremes and the fact that you treat them the same in?
Well, what we are saying is that I'm giving you a randomized algorithm, and this algorithm has a property that if you know, for any fixed D, and let us say for any fixed ordering of events, I will sample, so if this particular ordering is possible in a linearization, then I will sample some linearization with this ordering with probability at least that, that amount. It's a rather weak result. I guess what you're saying is that, well, there can be a particular ordering of D elements that has that occurs in many linearizations. And there is a different ordering that occurs in very few linearizations. And we're not sort of,
yes, but I think in a sense, because of the population of the set of equivalent behaviors, the measure of presence of one as opposed to the other one are exponentially different. So yes. The fact that now, but we are kind of saying that we will hit either one with the same probability seems strange a little bit.
Well, this is so. I mean, one other thing I guess that you're alluding to is that sampling uniformly from the set of linearizations of a partial order can be a hard problem, right? So if you see, our algorithm is very simple in its sampling thing, whereas you know that if you want to uniformly sample linearizations of partial order sets, that's a sharply hard problem. So
true, but I don't have to
will not be able to take into account these kind of how many linearizations have this ordering.
But I don't want to even uniformly sample. All I'm saying is that it should be easier to hit an exponentially large set, one of the members of an exponentially large set.
What we're giving is a lower bound, right? So we are saying that the worst case will happen with this probability, but it is possible that a particular thing is found with much, much higher probability. So maybe that answers your question, right? So this is a lower bound on the probability.
Okay, there is also a question in the chat. Is your tool applicable only for safety properties, or can it be applied for security properties as well?
I mean, this is a rather black box approach, right? So in some sense, we don't even specify what the property is. We say that, look, somebody designs a coverage goal, and that's where the randomized algorithm starts. So now if you have a security property for which you have somehow come up with the right notion of coverage, and of course, this coverage has to be somehow empirically correlated with the kind of problems you're expecting, then, you can design all these algorithms. I don't really, these algorithms don't care if it's a safety property or a security property or, whatever. Of course, we are still looking at finite samples. Each test, we are taking a space of tests, and at least in all these examples, each test runs a finite execution of the program. So this is not something like, oh, can you prove termination with these things?
Okay, so it's a good point now to stop the recording. Thank you everyone for attending.